Hello and welcome to the first of two videos on the Hadley Cell. In this video we're going to focus on the Hadley Cell structural characteristics, and in the second video we'll focus on concepts of absolute angular momentum and some of the variability that is seen with the Hadley Cell. So let's start with this depiction of annually averaged insolation. How much of the sun's radiation energy is reaching to the Earth at its top? If we look at this in the annual average, we see that the highest values given by the red shading here, over 400 watts per meter squared, so watts per unit area, is present here near to the equator, and it decreases as you go poleward in both northern and southern hemispheres from there, reaching below 200 watts per meter squared as you reach toward the higher latitudes. Now this is only how much is actually reaching to the Earth. A lesser percentage of this is actually absorbed by the Earth, about 70% near to the equator, and much less near to the poles due to the radiation effects, the reflecting capabilities of snow cover and ice cover that are typically present there. So again, summarizing, this annually averaged insolation or incoming solar radiation is maximized at the equator and decreases poleward from there. So if we ignore other processes for a moment, so if we ignore other elements of the radiation balance, how much comes in and is reflected, how much is absorbed, how much is re-emitted in the form of long-wave radiation, things of that nature, latent and sensible heating associated with phase changes and two air masses or air touching another surface with a different temperature, as well as transports both horizontally and vertically in the atmosphere. So if we ignore all of those for a moment here, this leads to the tropical atmosphere being warmer than at higher latitudes. So we get warmth concentrated near the equator that becomes less warm as you go poleward from there. So let's take a look at this from a thickness perspective. So if we assume hydrostatic balance, we can obtain this equation here, which is a form of the hypsometric equation. And on the left-hand side, we have the layer's thickness, the height of the second level minus the height of the first level, and that's approximately equal to the mean virtual temperature within that layer. We have this natural log that involves the two pressure levels. We also have constants for the dry air gas constant and gravity here. So we're going to take P2, that second pressure level, to refer to the tropopause, and Z2 to be the height of the tropopause. We're going to take P1 to be a near surface pressure level, like 900, 950 hectopascals, not specifically the surface, but very close to it at sea level, and thus Z1 will be the height of that pressure level. So we know that thickness is greatest near the equator because it is relatively warm. That layer mean virtual temperature over the depth of the troposphere will be highest near the equator, so we get this warm bubble that we see here. Conversely, it will be relatively cold at higher latitudes. Less radiation, less solar heating, less warm in terms of the tropospheric mean virtual temperature. So consequently, we get large thickness. The difference in height, that's depicted here on the vertical axis on this schematic, between the tropopause given by this top black line and the near surface pressure level given by this bottom black line is greatest. So Z2 here minus Z1 is larger than Z2 minus Z1 that we see here as we reach into the subtropics. So consequently, this results in relatively low pressures near the surface at the equator, relatively high pressures near the surface in the subtropics, relatively low pressures aloft in the subtropics, and relatively high pressures aloft near to the equator. And this matches pretty well with what we saw from our tropical climatology materials a couple of weeks ago, where we would see low-level anticyclones in the subtropics and upper-level troughs in the subtropics. So from a force balance characteristic, let's think about the wind initially being zero, no horizontal motion in the north-south or east-west directions taking place. So given that the wind is initially zero, there's no Coriolis force, which is directly proportional to the wind speed. That means that the horizontal pressure gradient between high and low pressure, both near the surface and aloft, causes the wind to accelerate from high toward low pressure. So consequently, we can add in these arrows here. Pressure gradient force causes the wind to accelerate toward the equator at low levels, so equatorward flow, and toward the poles, or poleward flow, near to the tropopause. However, once we get this wind in place, the wind speed is no longer near zero. The Coriolis force, therefore, becomes non-zero as well. It's relatively small in the tropics and becomes zero at the equator, but it's not small enough that we can completely neglect it from our force balance consideration here. So let's look at the lower troposphere here for just a moment. We've depicted our high pressure here in the northern hemisphere and in the southern hemisphere subtropics, with low pressure here near to the equator. And each of these black lines can be viewed as a different line of constant latitude. So this gives us our near surface pressure field associated with the Hadley cell circulation. We add in our purple arrows once again to depict the wind induced by the horizontal pressure gradient force from high toward low in both hemispheres. So this is bringing the air from the subtropics toward the equator in both the northern and the southern hemispheres. The Coriolis force then acts on this pressure gradient force. So initially the wind is exclusively from high toward low, but then the Coriolis force, which is 90 degrees to the right of the wind in the northern hemisphere and 90 degrees to the left of the wind in the southern hemisphere, directs this toward the west, so from east to west, given by the red dotted lines that I've added here. Now as we go forward in time, we get a balance achieved between the horizontal pressure gradient force, depicted here by the purple, from high toward low, and the Coriolis forces, which are to the right of motion in the northern hemisphere and to the left of motion in the southern hemisphere. So consequently, that gives us a wind that deflects toward the west, from east to west in both hemispheres. So you'd get a flow directed from east to west here, with the Coriolis 90 degrees to the right and the pressure gradient 90 degrees to the left under the constraint of geostrophic balance. Likewise, in the southern hemisphere, a flow from east to west, the pressure gradient force 90 degrees to the right, Coriolis force 90 degrees to the left under the constraint of geostrophic balance. Now when we add friction, things change a little bit here. Friction slows down the wind, which in turn slows down or weakens the Coriolis force. It doesn't change the horizontal pressure gradient force. That's related to pressure alone, not to friction. So that slowing of the wind reduces the Coriolis force, which changes that tug of war between the pressure gradient and the Coriolis forces, causing the pressure gradient force to win out. So instead of this gray wind that goes from east to west in both hemispheres, we're left with a wind that comes inward slightly toward areas of low pressure in both hemispheres. Still predominantly easterly, however, with a slight north to south component in the northern hemisphere and south to north component in the southern hemisphere. And this gives rise to the band near to the equator being known as the intertropical convergence zone, so named by being in the tropics with convergence associated with this friction-induced modification to the near surface winds. So if we put this in terms of the overall Hadley cell circulation schematic, we have this flow that goes from the subtropics toward the equator in both the northern and the southern hemispheres, associated with our easterly trade winds near the surface that would be coming out of the diagram and into your face away from the screen. These winds converge at low levels, resulting in forcing for rising motion or ascent here near to the equator. Given that we're typically dealing with tropical air masses that are warm and moist, this ascent often results in deep moist convection or thunderstorms, as we have depicted here in the schematic with the gray cloud extending to a very high altitude. Now let's take a look at what happens near to the tropopause. So here the pressure field is flipped. We have relatively high pressure near the equator, relatively low pressure in the subtropics. But the same force balance diagram and same force balance arguments can be applied here as well. Initially, the horizontal pressure gradient force accelerates flow away from the equator in both hemispheres. This is associated with that branch of the Hadley circulation directed away from the equator in both hemispheres. However, as the wind becomes non-zero moving away from the equator, the Coriolis force begins to deflect it to the right. And so we end in the northern hemisphere, and to the left in the southern hemisphere. So flow going away from the equator and deflecting to the left goes from west to east in the southern hemisphere. And in the northern hemisphere, flow going away from the equator deflects from west to east as well. So we get westerly flow in the higher altitudes within the tropics as compared to the easterly flow that we see in the lower altitudes within the tropics. And we'll talk about the formation of this westerly flow in a different context from absolute angular momentum principles as we get to our second video in this series. Now friction, unlike at the surface, is comparatively minor here. There is some friction between different air parcels, different constituents within the atmosphere, but it's much, much less typically than what you would see right along or just above the surface. And so consequently, we say that it has such a negligible effect as to not need to include it within our diagrams that we see here. So if we bring this all together, now we're looking at this upper troposphere or near tropopause portion of our Hadley cell circulation diagram. Flow is directed away from the equator in both the northern and the southern hemispheres aloft, coupled with the flow directed toward the equator near the surface in both hemispheres. That means that there must be air sinking between the two. This air coming toward the subtropics at higher latitudes or higher altitudes and latitudes sinks down toward the surface where it then spreads out and is directed toward the equator. Likewise, the same is true here in the northern hemisphere as well. So together we have ascent over the depth of the troposphere in the tropics and descent over the depth of the troposphere within the subtropics. You'll note this dashed line here in both hemispheres labeled trade inversion. This is associated with the trade wind inversion, which is a type of subsidence inversion, meaning that it forms because air sinks over a large vertical depth, and it looks much like the capping inversions that we would see in the central plains during severe weather season. We'll talk about their formation and characteristics a little bit later on in the semester, but note that this descending branch of the Hadley cell is directly responsible for their formation as well. So from here, we now want to consider how we can depict this Hadley circulation, not just from a thickness-based perspective, which takes in some measure of diabatic heating, typically that associated with radiation, as we demonstrated through our first slide in this series. We want to put this into a perhaps more complex, partially qualitative, partially quantitative framework to be able to help us diagnose and explain the Hadley circulation. So there are two ways that we're going to consider that can do this. The first one is this Cuo-Eliason equation, which we use to describe this meridional or north-south overturning, meaning vertical, motions both up and down, circulation associated with the Hadley cell. And in its final form, with a couple of approximations, it looks like this, where we have on the left-hand side, we have a term that relates to our vertical velocity omega, and in particular, how it changes in the north-south direction. And here we have a term related to our meridional velocity, v, and how that changes in height in terms of pressure. We have a couple of coefficients here, A and C, that are related to static stability, which is how potential temperature is changing with height, and inertial stability, which is related to rotation. We're going to assume that both of these are positive for the purposes of this argument here. On the right-hand side, we have forcing terms for this vertical and meridional circulation that the left-hand side describes. This H here is a diabatic heating rate, where positive values of H indicate warming. Negative values would indicate cooling. And in particular, this is associated with the meridional or north-south variation of that diabatic heating rate. And then here we have a momentum forcing term that is specifically related to how the zonal wind varies both in the north-south direction and how that varies with respect to height. So again, that left-hand side describes the meridional or vertical circulation, and the right-hand side describes the forcing, the diabatic heating in the first term and the momentum forcing in the second term for this circulation. So we're going to consider two scenarios here. We're going to take each of these right-hand side forcing terms in isolation. The first one, scenario 1, is going to be diabatic warming, positive H, centered at the equator. That goes to 0 as you go further north and further south from there. And then our second scenario is going to consider a zonal wind U that becomes more westerly or positive, given that that would be directed from west to east along the positive U or X axis away from the equator, both near the surface and aloft, However, we'll assume that it does so more aloft with the subtropical jet that we'll describe in a little bit more detail shortly than it does near to the surface. So let's start with the heating forcing term here. So for diabatic heating centered at the equator, where H is positive, as I've depicted here with this H much greater than 0 here to indicate that it is a large positive quantity. H becomes less positive along the y-axis in the northern hemisphere. It also becomes less positive along the negative y-axis in the southern hemisphere, but we're going to focus on the northern hemisphere for simplicity's sake here. So as we go along the positive y-axis to the north here, we go from something that is large positive to near 0. So consequently, we are reducing or making H less positive or more negative as y becomes more positive. So that partial derivative of H with respect to y is going to be negative. So back in our equation, A for our static stability and C for our initial stability, we said that those are both positive. So this means that to get the left-hand side to be negative to match that partial derivative of H with respect to y, the partial derivative of omega with respect to y must be positive, and the partial derivative of V with respect to pressure must be negative. So the former here, omega becoming more positive along the y-axis, occurs when omega increases along the positive y-axis. Omega being positive means descending motion. So this can be achieved by having ascending motion at the equator that then becomes descending motion at higher latitudes. The latter here occurs when V increases, signifying stronger northward flow, with height. So for instance, we might have flow directed from north to south at low levels and from south to north at upper levels. So consequently, we are going from something that is negative at low levels in terms of the meridional wind to something that is positive at upper levels. So V is getting more positive upward, but as you go upward, P is becoming smaller, so the change is negative, and we get a negative value for partial V over partial P there. So these are both consistent with the schematics that we have drawn here, where the flow is from north to south in the northern hemisphere near the surface, south to north in the northern hemisphere near to the tropopause, ascending motion near the equator, and descending motion in the subtropics. And you could make the same arguments for the southern hemisphere, but it'll be just a little bit different in terms of the outcome. But you still get that same general circulation structure that we are seeing here. So in the other case, the momentum forcing case of zonal wind becoming more westerly away from the equator and doing so aloft near the tropopause more so than near the surface. It's a little bit more complex. So we know from our earlier discussion about the Coriolis force and its deflection that the zonal wind is from east to west near the surface, near the equator. So that's along the negative x-axis. So the zonal wind is negative there. Here in the upper troposphere, we're going to assume that air is rising from the low levels to the tropopause and initially has a very small value for the zonal wind. It's mostly just been moving vertically and not horizontally. Conversely, we described before that the zonal wind becomes westerly, or from west to east along the positive x-axis in both hemispheres as you go away from the equator and into the subtropics. We're assuming that this value for the zonal wind is larger than what we see down near to the surface. We'll talk a little bit about that with the subtropical jet in our next video. So then we're also going to assume that near to the surface in the subtropics, the zonal wind is near 0. So in both cases, as we go from the equator to higher latitudes, near the surface, U is becoming less negative. Aloft, it is becoming more positive. Less negative and more positive have the same sign for the partial derivative of U with respect to Y. However, the magnitude of this change from near 0 to much greater than 0 versus slightly greater than 0 to near 0 is greater aloft here. So partial U, partial Y is positive in both cases, but partial P of that quantity is negative because the value is increasing going up as pressure goes down. So the right-hand side of that equation is negative in the northern hemisphere from this forcing term. So this necessitates the same sign for partial omega partial y and partial v partial p as we saw for the heating forcing. So this occurs when omega increases, going from descent near the equator to ascent at higher latitudes along the positive y-axis, and when v increases, signifying stronger northward flow aloft as compared to the southward flow near to the surface. However, the difference between the heating term and this term we're already assuming some structure to the zonal wind in association with the Hadley cell. The former, when we were looking at heating, we assumed no particular structure to that heating apart from what the sun already provides to the earth. So there's a little bit of assumption that's going into this depiction here. Finally, we come to our last of our perspectives for the Hadley cell in terms of diabatic heating, and this is associated with our simplified model set known as the shallow water equations that we first introduced during our equatorial waves lecture. So we're going to apply a steady diabatic warming, whether that's associated with solar radiation or from latent heating or some combination of both. The source of it is not as important right now as the sign of it is. We're going to center it on the equator, so similar to what we would expect from the radiation budget alone, where it's maximized at the equator. And we're going to put that into the simplified equation set. And lo and behold, the solutions to that, when we average them across all longitudes, so around the Earth, at and near the equator, we get an approximation for the Hadley cell. I'll start with this second panel here, known as the stream function. In this case, it's defining the rotation in the y and z axes, very similar to the cartoon on the previous two slides. So here we see rising motion near the equator, where the diabatic warming is taking place. We have motion coming from the poles toward the equator near the surface in both hemispheres, and flow going away from the equator toward the poles near to the tropopause in both hemispheres, with sinking motion in the subtropics in both hemispheres. The diabatic warming results in a broad negative pressure perturbation, so locally low pressure here near the equator that becomes less negative as you go further away from the equator. The top panel shows our zonal velocity, our u-wind component here. It's very near zero here at the equator in both near the surface and the tropopause. However, we see easterly winds just north and south of the equator near the surface, and westerly winds just north and south of the equator in both hemispheres. And this is very consistent with what we saw in our cartoon schematic, how we obtained it through the Cuo-Eliason equation, how we obtained it through thickness perspectives. However, I'll emphasize that this only captures about 30% of the observed Hadley cell's intensity. It relies on heating being centered at the equator, maximized there. In general, heating is not always centered there. It moves north and south with the seasons, as the circulation features move north and south with the seasons. And so to get a better depiction of the Hadley cell circulation, we need to take into account the fact that the heating may not take place just right at the equator, but rather may take place off of the equator in some form, and it can also change intensity. As we get later on in the semester, we'll be able to show how taking that into account leads to a stronger Hadley circulation that more closely resembles what we actually see within the atmosphere. But for now, that closes up our discussion introducing the Hadley cell structure and ways in which we can represent it with simplified equation sets. As we move into our next lecture, we're going to look at some additional characteristics related to the Hadley cell, namely absolute angular momentum and its conservation, giving rise to the subtropical jet, as well as the variation that is typically seen with the Hadley cell.